Okay, hi everybody. I hope everyone can hear us. Welcome, and thanks for joining us for the Series 3 of the webinars that we're going to be doing as part of Sustainable Preservation Practices for Managing Storage Environments. We're here in Rochester, New York in the USA. Again, just thanks for joining us from wherever you are around the world. I know we hopefully have some folks joining us from overseas. I noticed a few people from Australia in the registration list and a few from Nigeria. So if you're up at 2 o'clock in the morning and listening to us, hang on one second. We've got a few audio issues that Chris is going to take care of in the background. But if you're up at 2 o'clock in the morning, wherever you are, I do promise to do my best. I'll be the presenter today. My name is Jeremy Linden. I'm the Senior Preservation Environment Specialist here at the Image Permanence Institute. And joining me in the room is Chris Cameron. He's our Sustainable Preservation Specialist. Chris is kind of running the show in the background, so he's taking care of all the technical aspects of what we're doing. And if you send in questions or anything through the chats, Chris is going to be the first one to catch that and put it through. So thank you very much. And moving on just a little bit, some kind of housekeeping stuff and technical support. Just so you know, for anyone who's trying to get in on wireless or on dial-up, we do apologize, but the streaming speed for the webinar can be rather slow. If you have it available, a wired connection is preferred. And for the audio, I know some folks are already having a couple of problems with the webinar audio so far. But with the audio, you can either do it through the computer on VoIP, or if you're having trouble with that, feel free to call in via telephone. There is a toll-free number below here, and I'll read that out loud for anyone that's having issues. It's 1-314-627-1518. That you can call in and join the webinar in a conference call. The access code and that phone number are both provided to you as part of your registration email, so just go back to the email that you used to sign in and you'll be able to get access to that information. Now, if anyone's having technical problems that are sort of a greater nature than what we just talked about, Lauren Parrish here at IPI is available in the background as well to help us out with any technical issues. And her contact information is lmppph@rit.edu. Or she can reach directly on the phone at 585-475-7175. And just as kind of a heads up as we go through today, we've got a lot of information to cover. We're going to do our best to squeeze it all into the hour and a half. But just because of the way the software is running, I won't be able to catch the questions immediately as they come through. As I said, Chris will be reading those initially. So if you have any issues or any questions or something that you'd like us to talk a little bit more about, feel free to submit those through the questions box over on the right-hand side through the webinar software. And as I said, those will come in. We'll probably won't deal with too many as we go through the content of the webinar today, but we did leave some time at the end of this to try and get through some questions and just talk a little bit more about any specifics that you're curious about. So please do feel free to send those in, and we'll cover what we can. What we can't get to during the webinar, we will be in touch with you after the webinar to make sure that most of your questions are able to be answered to our best ability. A little bit of background on us here at the Image Permanence Institute. As I said, we're situated in Rochester, New York. It does not look like that outside today, although we do have somewhat of a rare winter occurrence here in Rochester today where the sun is actually shining. We've got a couple, 3 feet of snow on the ground in different parts of the city, but the sun's out and it's a beautiful day. So we're here at Rochester Institute of Technology, and our IPI is a nonprofit research lab that was founded in 1985. We're excited to be celebrating our 30th anniversary this year. Preservation environments and sustainability is a part of what IPI does, but on the right-hand side of the slide, you'll see some images of different ovens that we use in accelerated aging testing and some of the research that we do here at IPI. And we still do an awful lot in terms of looking at preservation issues and photographic images or other image media. So there still is a lot going on with sort of the original intent of IPI as well. Just about the series and what we're working on, this is the 3rd time that we've had the real fortune of being able to give this series of workshops and webinars. This is the 3rd time that the National Endowment for the Humanities has funded this program through an education and training grant. We first did this back in 2011, and we're excited. It's nice. We just made it through a series of a couple of other aspects of the webinar, or a couple other aspects of the series a few months ago. But I wanted to say real quick, and this is just that question of how is this going to be a little bit different, maybe from what you've heard before here at IPI, or from another preservation seminar or webinar that you may have attended in the past. And I want to focus on a couple of things. One, this is not simply going to be a look at what are the appropriate preservation conditions, or how do I preserve or conserve different types of media or materials, especially not today's session. What it is that we're approaching and what it is that we're trying to do, really, is to look at preservation environments and look at building operation as a holistic idea. And the goal here, really, it's available on the screen, I'm not going to read it verbatim, but the idea behind this is that we want to create an environment, or help institutions create an environment, where the collections care, interests, or side of the institution, and the staff who are responsible for taking care of the building and creating the environments that the collections live within. Those two groups need to be able to work together and have a common ground and have some common language and some common knowledge that they can use to move forward and achieve what we're now defining as an optimal preservation environment, and to be able to sustain that idea. And it's a slightly different approach than what we've taken in the past, or sort of than what preservation management has taken in the past. It's very easy to become siloed in our profession and kind of look back and define what it is that we need in terms of the collections and in terms of preservation, without always having a full understanding, or at least a broad understanding, of how that fits into institutional operation, or what it is that is required institutionally in terms of buildings and mechanics to make that environment happen, or to make that preservation environment the best that it can be. And that's our goal for this series. It's something that we talked about in the earlier part of the series, but it's something we're going to focus on here for these next series of webinars, is how do we go about that? What information does everyone need to have? What are some of the details and some of the options and strategies that people can use? And it is just that. We're looking to provide that balance. It's realizing that there are really two sides of the coin here, that preservation is not created in a vacuum, and that buildings operation and how it is that a system runs can't be done without some knowledge of what it is that the collection needs, not only what it is, but also what it needs. And as we break it down, today's session is going to be a little bit different, but as we break it down throughout the series, our goal really is to try and set out and lay out some practical guidelines for thinking about risk as it may be posed to collections, and what it is that we can do to try and mitigate that risk as we move through and try to experiment with some different energy management practices in today's day and age. I won't go too far into the topic of just sustainability in general, but the idea here is that it's a hot topic, right? We're in a world culture right now where sustainability is a concern. The interest in renewable energy is certainly there throughout the world. And we're dealing with situations where energy costs and operations are becoming a significant aspect of institutional budgets, and in many ways are sort of driving institutional missions or institutional operation, in the sense of how do we go about cutting costs and still providing the same amount of, or the same level of service and access as we have in the past. So the goal here is to think about that goal or that need in terms of sustainability and in terms of reduced energy consumption, and how it is that our collections environments, or how it is that we as collection professionals can participate in that mission without or with being able to control the risk that is placed on collections as part of that process. And this is, as I said, this series of webinars that we're starting out today is really a follow-up to what we've been doing for the last few months. We've been working on this particular project since early in 2014. But from September 2014 until just this past January, we were giving a series of 2-day sustainability workshops on site throughout the United States, 2 days apiece, where it was pretty intense, really. We went through for each of those 2 days, and for give or take about 8 hours a day, really focused in on a lot of things concerning sort of the background of degradation, how it is that materials decay, understanding documentation, where we get data from, how best to get data, talking about data analysis, talking about mechanical system operation, and talking about what are some of the options or strategies that we can use in mechanical system operation to save energy without impacting the preservation environment, or in many cases, actually improving the preservation environment at the same time. And that was the on-site portion of what we were doing in this particular series. Now coming up through October, we'll have 9 sustainability webinars that we're going to talk through. As I said, we start here in February, and each month is going to be on a slightly different topic. For this one, for what we're doing today, really is, I'm just going to put it out there, and this is fair warning to anybody who's joined us for one of these in the past. This is really meant to be an overview of some different aspects or some different things to consider when it comes to sustainable preservation practices. And this is really designed as an introduction, or for people who have participated in before or may have heard us speak in the past or attended a workshop or a webinar before. It may be a refresher or a review for you. Our goal with this series is really to try and delve in a little bit deeper into some of the details that we couldn't cover in those 2-day workshops on site. So you're going to hear some different information from maybe what we presented in the past. But for today, really what we're trying to do is introduce the rest of the series. We're going to talk through some of the overarching themes and ideas and talk about what it is that we're going to work on as we move through the next 9 months, give or take. So one thing to keep in mind is, please do be patient. This may be a review for you. What we're hoping is that overall the series is meant to be able to stand alone in many ways. It's not required that you attend every session. You won't miss anything by not attending each session. If there's one that's particularly interesting to you, please do feel free to just join in for that particular webinar unit. But that being said, it will build on itself as we move through. You'll notice on the website, if you go to for registration, that a few of these are really meant for introductory audiences, maybe folks who haven't given a lot of thought to this before, with a lot of the very high detail or actual getting down into strategy and practices and procedures coming a little bit later on in the series. And we'll talk about that a little bit more as we get further in. But for today, what we're going to cover and what we really want to go through is this idea of what are these overarching themes? What is it that we want to keep in mind as we move through this process? And what are sort of the big ideas that it comes down to that make sustainable preservation and sustainable preservation practices possible? What do we have to think about in order to get there? And the list here on the screen is a good start. We're just going to kind of jump into it and go from there. The first thing really is to define what it is that we're talking about, to give some thought to, all right, what is it that we're trying to achieve here? And a few years ago, we sat down here at IPI, and a lot of people have given this thought all over the world. It's not to say that it's just happening here. But when we sat down and tried to think about it, we were up against the challenge, really, of thinking about this in terms of, well, how does the current research and how does this sustainability need make our job or make our mission as preservation professionals different from what it used to be? And how do we come to a compromise, or how do we come to some sort of agreement between what can sound or feel like two very, shall we say, polar opposite ideas? For many years we've been running preservation environments with the idea that we needed flatline conditions, very steady state environments with constant airflow. And without fail, that definition of mechanical operation is oftentimes very energy intensive, for lack of a better way to put it. And the question there is, well, is that, given the research that we have, is that still the case? Are there things that we have to rethink in terms of the necessary environment and necessary operation? And are there ways that we can cooperate with this overall idea of sustainability to try and make it so that our storage environments, so that our display environments or our gallery environments are not exceptions to the overall mission of trying to find sustainable operations, sustainable options for today's institutions? We want to be a part of the solution, really, not a part of the problem. And what we sat down and agreed on, and this is our working definition, is that we want to think of this as an optimal approach. We want to try and find this optimal environment where we can achieve the best possible preservation of collections as we understand it based on today's research. But we want to do that with the least possible consumption of energy, which is a challenge in and of itself. It's not to say all the time that it's going to be an incredibly small amount of energy that creates that environment, but even so, we're looking to see if we can find a comparatively less amount of energy to use to create these preservation conditions. But in this goal, when we're thinking about that best possible preservation and least possible consumption of energy, we want to make that process sustainable. And this is something that I think is necessary to really think about and define here for just a second. It's far too easy in all of our roles, and I'm hoping that we're joined here not only by some preservation professionals, but also by facilities professionals as well. I'm really hoping that, when we sit down and think about it, one thing that we find, and one thing that is typical in our work environments, is that we approach things on a project basis. We define a goal, we identify what the work is or who the people are that are necessary to achieve that goal. We do the work, we work through the project, and when it's done, we've discovered or we've found or we've achieved an outcome. And we're moving on then to the next project from there, right? Oftentimes we sort of wrap that one up, close it up, and move on to the next thing. And instead, when we talk about preservation environments and optimal preservation environments, one of the things that we've learned, and this is through years and decades of practice and experience and just talking with other professionals in the field, both on the preservation and on the facility side, is that this has to be, in order to make it sustainable, this practice has to be part of the institutional culture. It's not something where we achieve a goal or where we finish a project and then we move on to the next thing. But this is something that becomes encompassed into the overall institutional operation. It's basically a change in the way that we do business. And that's a lot of what we're going to talk about throughout the series, is how do we go about changing our work culture in some ways, in terms of communication, in terms of documentation, in terms of teamwork and practices, to make sure that when we figure out what some of these sustainable operations options are, and when we get a little bit closer to this optimal preservation environment, how do we create an institutional culture where we can sustain that operation and that practice over time? And that's really part of the end goal, is not just figuring it out one time, but figuring it out how to do it over and over again. So the baseline requirements, what do we have to do in order to achieve that optimal preservation environment? Well, we need a team approach. This, the saying goes, it takes a village, if you will. But the reality is it takes a lot of different people within an institution to make this happen. And this needs to be measurable. We need access to reliable data about the collections and about the storage and display environment in order to be able to gauge what the impact of some of our changes or some of our decisions is. Going through and trying to make sustainability changes or make energy changes or preservation changes to an environment where collections live is all well and good, but if we can't measure the difference that occurs or the consequences of our actions, then it's awfully hard to say what benefit or maybe what negative impact we may have had based on a certain test or a certain procedure. So we have to have reliable data, and we have to have a way to analyze that data. On top of this, we need to have a good understanding of mechanical system capabilities and performance, and we'll talk a little bit more about that later. But the idea here is that walking in, we oftentimes fall into a culture, and I'll say this on the facilities side of the coin, and I do have a little bit of experience there. But on the facility side of the coin, we fall into a culture where it's truly reactionary. We try to fix things. When something breaks, it's defined as being broken, and you go out and you fix it, you repair it. And as long as no one is calling or submitting a work ticket, then that is oftentimes the definition of success. And we want to move beyond that a little bit and try to achieve a proactive understanding, a holistic understanding, if you will, of not only how the mechanical system operates, but how that operates in conjunction with the building envelope capabilities, with the patterns and work areas for staff or what places are people occupied, and with the needs of the collection in terms of preservation requirements and how materials degrade over time. So we'll spend some more time on that, not only today, but also in future webinars. And finally, we have to have that ability to define and achieve what it is that we're thinking of as optimal. And maybe the underlying theme there is just to realize that optimal in and of itself is going to be different for every institution out there. What is optimal for the Library of Congress may not be optimal for my local historical society. But that's not to say that both of them can't achieve optimal. But optimal just looks different for each institution. It's based on the capabilities of your building. It's based on the needs of the collection and what the goals of the institution are. And it's based on the availability of mechanical operation, mechanical systems that can control environments. Optimal for a building without any mechanization at all is probably going to look a little bit different than optimal for a facility that stores acetate film in frozen conditions. So we want to accept that and kind of use that as an overall understanding that each institution has to reach that definition of optimal, or what it is they're trying to achieve for themselves. So the first step in this process, what is it that we have to think about? Well, this environmental management team, right? This idea that it takes more than just one person. And where this really comes from is if we sit back and think about it, we realize and we find that the environments that are within our buildings truly have multiple determiners. It's not any one person or any one institute or any one aspect of the institution that gets to decide exactly how a room operates, especially not when it comes to collections. So on one hand, we have the people who are responsible for providing the environment. We have our facility staff who are the day in, day out caretakers of the equipment and of the structure of the building itself, who are going to determine not only what the equipment can do and what the environment is that it can create, but will also have the best information or hopefully access to the information of what the system or what the building may be capable of. So if what is currently being created in terms of the environment isn't what we're looking for, is there an opportunity there to do any better? So they have sort of, if you will, one spoon in the pot. They're one of the cooks. But on the other side of this, we also have our preservation professionals, right? We have those of us out there that are responsible for understanding the collection, knowing what it is that we have, and defining what it is that that material or media needs for long-term preservation. What are the conditions that are required to make sure that decay is slowed down as much as we can possibly make it? And oftentimes in the past, this has taken the form, excuse me, this has taken the form really of providing a series of set points. These are the conditions that the collection should be at. And we're going to define those as a certain temperature and a certain relative humidity. And those get passed off to the facility staff, who then are tasked with trying to figure out how to create it and whether or not that's even possible, given the building and the mechanical system that they're working with. Well, as a different approach now, this is not necessarily things that are being determined in a vacuum, things that are being determined by an individual group. It's looking at it from the aspect of everyone who has a role in this and being able to communicate and say, well, what can we do? What is the best that we can achieve? Another factor that comes into play is, are there people present where the collections are? Do our staff have to work in those environments? If so, we may not be able to make them as cool as we would like to have them for preservation. Or are we in a situation where we're working in a gallery environment, and human comfort in terms of our patrons and our public who come through and view and look at the materials? Are we worried in that circumstance for their comfort or their concerns or their needs? And that takes a whole other role into play. We've worked in institutions before where union staff were involved, and there were specific requirements from the union workers of what appropriate work conditions were and what weren't. So again, it takes into account, or it comes into play, what it is or who it is that works in that space or works with the material where the environment is being created. And finally, kind of overarching all of this, and this is one that we can sometimes lose track of, but overarching all of this is that idea that there's an administrative component here as well, in that in today's day and age, as energy costs generally across the board are rising, that there are decisions, hard decisions, that have to be made at administrative levels that have to do with how much can we actually spend on utilities budgets. So we've been faced in the past with institutions or circumstances where during hot or wet summer months, institutions have to make the difficult decision to back off on environmental control to make sure to hold a higher air conditioning set point, or allow the RH in an environment to go up, because they simply can't afford the energy component that it takes in order to create the appropriate preservation environment that we were looking for. So that comes into play too. It's understanding what the institutional resources are that you're working with, and whether or not it's even possible, not just from an equipment standpoint, but from a financial standpoint, to create the appropriate preservation environment. And all these different factors come into play, and they all have to be taken into account when we're thinking about what that definition of an optimal environment is for the collection. Optimal doesn't just mean the best preservation again. It means that best preservation that also matches or fits with the other institutional needs and priorities. So when we think about who needs to take place, or who needs to take part, on that team, when we're thinking through, what we find really is that there are a number of different roles within an institution that can fit what it is that we're trying to achieve. On one hand, we've got folks from collections care and preservation that are tasked with understanding what we have in the collection and what the needs of that material or media is. And they're the ones that are going to be able to sit down and talk through, all right, what are the temperature and relative humidity conditions that we have to shoot for? And what are the ranges? We'll talk a little bit more about that today, but what are the ranges or what conditions might be acceptable or safe? Or what should we strive to achieve in different seasons or different outdoor climates? And as well on that team, we may have representatives from the facility staff or representatives from operations or institutional planning sometimes. Oftentimes part of that team may be a sustainability manager for an institution if there is one. And they have the role of bringing to the table that information about how the building runs, about what the infrastructure is that we're working with, not only in terms of the building itself, but in terms of the specific mechanical systems that serve where the collections live. And when we get into the realm of sustainability officers or sustainability managers for institutions, oftentimes they're the ones who have the understanding of the overall administration goal of what the institution expects in terms of its green approaches or its green strategies or what they need to achieve for sustainability purposes, be it financially or just be it from an environmentally responsible perspective. So those goals can be brought forward to the table from that side of the house. And finally, there has to be representation there also on that team from the administration, from that institutional high-level perspective that understands not only what the goals and what the mandates of the institution are, but also can approach it from the perspective of what are the resources at hand, what is it that we have to work with, and if we need something more than what we've had in the past, how might we go about finding those resources that may not have been there or existed before? What are our options? So just to run through again real quick, the collections folks, what do they need to know? Well, what are the specific conditions that we need for ethnographic materials? Or if my collection is book and paper, what are the environmental conditions that we need to have for that? But beyond that, a lot of this is sort of the data provision part of this. In the past, and I think as a field, we've gotten a lot better at this, understanding what the environmental conditions are that collections live within, being better at analyzing, being better at data logging. This is something that as a profession we've gotten a lot better at in the last few years, or at least the past decade or so. And that data about what it is that the collections live in every day. What are the trends for temperature and relative humidity? And frankly, what is the impact of that temperature and relative humidity as well? That's something that the collection staff is tasked with knowing. It's something that we are the closest ones to the needs of the collection, and when we come to that table and have that discussion, we have to be able to talk about what are the consequences of holding a certain environmental condition as opposed to another one. And beyond that, it's understanding what those pressing risks are, understanding what it is that could go wrong if something either continues as it is or if we don't make a proper choice in terms of management or environmental control. These are the situations where if we understand that know that there's a mold outbreak in our one storage area every spring, these are the folks who are going to know, and that's what we have to bring to the table. On the facilities side, really, this is that expectation that they're going to be able to bring that mechanical operation and that system capability to the discussion, understanding not only how it's designed and what it's capable of, but also understanding how it currently runs and what it's typically being asked to do. Because what we're talking about in this process is exploring the possibility of doing things a little bit differently. And this kind of goes back to that reactive versus proactive discussion, which is just to say that oftentimes this takes an approach or it requires a little bit of work that is maybe not the normal part of what we might do on the facility side of the house. Fixing things is one thing, but oftentimes it's been a long time since someone in the department went back and looked at the original design intent or the original design capability of a particular system. And that's part of what we want to do in this process. These folks also have to have the authority to carry out team decisions. They have to be able to make the changes that are necessary to bring into play or to actually carry out some of the changes that we're thinking about, whether it's just changes in operations, whether it's changes in set points or operating time. And one aspect of this as well is that as a group at the table, as the team, we have to be able to come to some clear operating goals that can be communicated and laid out in terms that can then be acted on. So this may be, again, a continuation of, well, we need a series of set points, and maybe those set points look different than they did before, but we have to choose specific numbers and specific ranges that the system can be told and programmed to then do. The role of the administration in here largely is really support. It's coming at it with that institutional overview and being able to provide the mandate and the encouragement for the team to go about this work, make sure that everyone has the responsibility or it's recognized that this is a necessary approach or a necessary task for this particular group. And again, that resource, looking for those resources, whether it's just allocation or whether it's thinking of new and different resources that might be tapped into to achieve some of the work that we're looking at. What does it take for this to actually succeed? Well, it's fairly simple, really, when you lay it out, but I don't want to understate it. There's a commitment to improvement here that really has to be recognized, and oftentimes it has to be taken on by the institution. This is that larger administrative aspect of the goal, or the oversight has to be that we want to make a change, that we want to find a more sustainable or a more optimal way of creating these environments and not make the choice of preservation versus sustainability, but find something in here and make sure that we approach it in such a manner that we can try to do the best job that we can for both of those. This entire process takes someone with motivation. It takes a leader or a champion, if you want to put it that way. And that person can come from just about anywhere in the house. I've seen it come from preservation staff. I've seen it come from facilities staff or sustainability managers. But it takes someone to get the ball rolling that's going to bring everyone together and have these conversations and go through this process. You know, it's necessary to keep that energy there because we all are very busy in just our everyday jobs with a lot of different things pulling at us. So someone has to take this and make it their own and really move forward with it and encourage everyone else to continue through the work and make sure that we're communicating and moving along these processes. We need to have the tools and the infrastructure available to gather the appropriate data and information that we need, not just in terms of environmental data, but also in terms of data related to the mechanical system. And we have to have regular opportunities for communication to make sure that we can review and analyze the data that we've gathered. And finally, we need to have an agreed upon process for, as we do the analysis and think about the environments and think about energy consumption, we have to have an agreed upon process that we can go through and test some different strategies or actions for improvement that we think may make a difference. And that has to be agreed upon. It has to be reviewed. We have to look for the consequences of those changes. And this is a constant check and balance system, if you will, in the sense of making sure that we don't just implement a change and walk away from it and assume that it's going to work perfectly fine. But we want to implement a change and we want to go back and look at that change within a short period of time and make sure that everything is working as we want it to, or make adjustments if it isn't. So the second part of what to do today, and this is where we have to stress the overview part, we'll discuss, excuse me for one moment. We'll discuss as we go through, I think in the second and fourth webinars a little bit more, we're going to be looking very closely at how it is that materials actually degrade over time. The three environmental factors that we're most concerned with here are temperature, relative humidity, and dew point. Now, there are a lot of other environmental factors that come into play. Light, pollution, both come to mind. And there are factors that we want to consider, and we will talk about a little bit more as we move through the environment or move through these different series of webinars. But for today, we really just want to stress these three initially because they underlie an awful lot of the degradation or an awful lot of the decay that we typically see among collections and environments. So the first point just to talk about or make sure that everybody's familiar with is this idea that temperature, relative humidity, and dew point are truly interrelated. You can take any two of these numbers and figure out the third. So if I have a temperature and relative humidity, I can solve for dew point. And at the same time, we also want to remember or keep in mind, I'll just say this as an overview, and it will come into play when we talk more about dew point later, is the idea that when we have a constant moisture content in an environment, or when we have a constant dew point, as we raise the temperature of an environment, the relative humidity will go down. And as we decrease the temperature in an environment, the relative humidity will go up. So there's this relationship between the three, that any two of the three determine a third, and we want to make sure that we understand how that relationship works. In terms of degradation or decay, where this really comes in, or the significance, is that temperature in combination with relative humidity really has the biggest impact on what we're going to talk about as chemical decay. And that's the aspect of looking at it and saying, trying to identify which one of these things we want to pay the most attention to when thinking about different modes of decay. Relative humidity, as we talk about that, we're going to be looking at different significant roles that it has in mechanical and biological damage, but also the role that it plays in metal corrosion. And really, dew point is kind of the overarching significant theme behind it all. The idea behind dew point is that looking at the moisture content in an environment very quickly allows you to be able to determine what kind of an environment you'll be able to create. Dew point truly does determine the temperature and relative humidity combinations that you can achieve for any given indoor environment. Temperature, just by means of definition, is a measure of heat expressed in degrees Fahrenheit or Celsius. I will warn everybody that I will most likely talk through most of the webinar in Fahrenheit today, although we will include Celsius information for later webinars when we get into more detail. The thing about temperature is that it's very easy to measure, right? Thermometers have been around for a long time and they're highly accurate. And today, data loggers, temperature is usually the least of our concerns in terms of calibration and accuracy. From a mechanical perspective, from the facilities perspective, the interesting thing about temperature is that it's relatively easy to control. We have a lot of experience with it, a lot of engineering experience. We've been doing this for a long time. And the nice thing is that from an energy perspective, it's usually the least energy intensive aspect of what we do between moisture control and temperature control. So that has that going for it. Temperature, we can do an awful lot with. Temperature fluctuation, when we start thinking about what happens, the risks here largely are these truly wide and frequent fluctuations that we may see. And by wide and frequent fluctuations, we're talking about 30 and 40 degrees over relatively short-term periods. Can have impact on some very sensitive material and vulnerable objects. But the reality for most materials in terms of looking at chemical and natural decay is the key is overall seasonal high and low temperature extremes. If we have a period of time where we run high temperatures for a long period or just on a consistent basis, then that's going to have a very negative impact on our ability to slow down the rate of decay. On the other hand, if we can have an environment where we can keep low temperatures for a longer period of time, then that's going to have a beneficial impact on our rate of decay. And that's what we want to think about in terms of control, is not necessarily worrying so much about small or minor fluctuations, and we'll get into this a little more with the standards discussion, but looking at it in terms of what are we able to do on a seasonal basis, or what are we able to do to mitigate these extreme conditions. Relative humidity is just a representation of how saturated the air is with water vapor. So when we look at relative humidity and think of it as a percentage, basically one way to approach that is that if we have a particular temperature, let's say that we're working at 70 degrees Fahrenheit or 20 degrees Celsius, and our relative humidity is 50%, then that essentially means that the air is 50% full of the moisture that it can hold at that particular temperature. And that's one thing that we'll find is that at different temperatures we can have 50% at 40 degrees or 50 degrees or 60 degrees Fahrenheit, and that always relates to the relative saturation of the air. Now, the relative humidity essentially determines the amount of water that's contained within collection materials. The relative humidity is what the material itself will come to equilibration with. So if we have a high relative humidity in a given preservation environment, if we're at 65% or 70%, eventually the collection itself, the materials, will come to full equilibration with that RH condition. And that's the concern, is that the more saturated the environment is, the more relatively full it is with moisture, that collection of that material is going to feel that same condition and will have negative or potentially positive impacts as a result. We'll talk more about that. Now, RH is a little bit harder to understand, and one thing that I do want to say just as a disclaimer here is that this is not the full temperature RH and dew point discussion. We'll go into that in a later seminar. I think the webinar for that is going to be maybe in February. But it's a little trickier to think about just in terms of what it actually means in terms of total quantities of moisture, because it's not a static figure. As I said, it's simply that relative saturation, and that can mean there's a lot of moisture in the environment, or it can mean there's very little moisture in the environment, depending on temperature and dew point. The other thing about relative humidity is because it is moisture saturation, it's a lot harder to control. It takes different equipment, it takes different types of work, and that control generally tends to be energy intensive. You know, we're talking in this circumstance about either removing exactly the right amount of water from an environment to achieve a relative humidity at a given temperature, or adding exactly the right amount of water in a given environment to create the right RH at a particular temperature. So this is, from a mechanical perspective, a little bit more tricky. And it's something oftentimes that for the facilities folks is just, you know, kind of the big part of what we're really trying to figure out how to do when it comes to collections environments. Temperature is fairly easy to create, but achieving that right relative humidity, which is based on the dew point, can be something of a mechanical trick, and oftentimes, as I said, is very energy intensive and is the larger part of the total dollar amount that we have to use in order to create these environmental conditions. RH fluctuations, the key here really is that it's the high and low extremes and that are prolonged for a period of time that we're really concerned about. We'll talk a little bit about equilibration in a few minutes, but the idea is that the high and low RHs, these short-term fluctuations, oftentimes collections don't feel them. But we are worried about these long-term seasonal changes. And as we have these long seasonal changes, you know, extended periods of either high RH or low RH, where there's time for the material to come to full equilibration, it increases the risk of mechanical decay. And two things can happen. If we have low moisture content or low relative humidity in a particular environment, materials can become brittle or they can shrink. On the other hand, they can also expand or warp due to high moisture content. And when we're dealing with high moisture content as well, we start to worry about issues such as metal corrosion and die bleed. Now, metal corrosion is a chemical process, not a mechanical process, but there are a lot of different things that can go on based on levels of relative humidity. Dew point, as we think about it, really is simply a measure of the absolute amount of water in the air. Now, we think of dew point as a temperature, and what we're defining there is essentially the temperature at which the air is fully saturated. So, you know, we're thinking about the total amount of moisture, and one thing that I want to throw out there is that in general, a high dew point condition, if we have a dew point, say, of 65 degrees or 70 degrees Fahrenheit, or, you know, call it 18 to 20 degrees Celsius, if we have that dew point condition, that's going to imply that there's a lot of moisture available in that environment. In general, warm air can hold more moisture than cold air. Whereas if we have a very low dew point, if we have a dew point that's around 0 degrees Celsius or 32 Fahrenheit, then we're talking about an environment with a relatively small amount of actual moisture that is held within that particular volume of air. And one thing to keep in mind as well is that when we're thinking about structures, without humidifying or dehumidifying or adding humidity or removing moisture from the environment, the indoor dew point is typically going to match the outdoor dew point. They do remain the same. So if we have an institution that, or a building that has no mechanical intervention and is just coming to equilibration with the outdoor environment around it, we're going to be able to look at that and oftentimes see that the dew point indoors is the same as what's going on outside. As we said before, as the air heats up, as we get a higher temperature in a given environment, the potential to hold more water exists. And again, one thing that we want to keep in mind is that even not only with the higher the dew point is there more moisture contained in the environment, but the higher the dew point, the association here, the relationship with temperature and relative humidity, means that at high moisture contents, it's very hard to keep a cool temperature and maintain a moderate relative humidity. In fact, it's relatively impossible. So when we think about it in terms of collections environments, we do really want to approach it from the aspect of low moisture contents or lower moisture contents. And controlling that dew point is what we have to do in order to achieve the cool temperatures and the moderate RHs that we're going to talk about finding for collections preservation as we move through. Now, on the preservation front and thinking about decay, really here at IPI, we think about and approach decay, at least on an environmental basis, really through 4 primary pathways. We'll talk about it in terms of chemical decay or natural aging is another way of putting it. Mechanical or physical damage or mechanical expansion and contraction, biological processes that can act on materials, and finally corrosion, which applies to metals and looking at that chemical process as well. chemical decay really is focused on organic materials, and by organic, we're not talking about sort of new wave kind of crunchy thinking. We're just talking about materials that are carbon-based. So this is largely, a vast majority of what we tend to deal with in cultural collections. It encompasses everything from plastics to paper, to different media types, to ethnographic materials, to biological specimens. All of these fall underneath this category, if you will, of organics. The areas that we aren't so much concerned with when it comes to organic decay or chemical decay oftentimes comes down in this broader definition. When we're looking at geological samples, it's a little bit different, or when we're working with metals, it's a little bit different, but we'll talk about those in a moment. But this organic decay, or this natural aging, is this spontaneous chemical degradation that happens as a combination of moisture and whatever compounds make up that organic material that are driven, that rate of decay is driven by temperature in the environment. So it is both of these aspects that play a role. It's temperature that drives the rate of that chemical equation, or that chemical process. And it's relative humidity that, if you will, serves as one of the reactants in that process. And as a rule, this is just the way it works. The more moisture that's present, the faster that rate of decay will occur. And the less moisture that we have, the slower the rate of decay will occur. What it comes down to is the objects are simply reacting with the environment around them. It's the air that the temperature and the air condition that they exist within. It's the moisture contained within that air. But it's also contaminants, and it's also pollutants, and they do play a role in this. Some of these reactions are quite slow. Others are very, very rapid. Again, it depends on what material it is that we're working with. One thing that is oftentimes quite obvious is that if we're familiar with sort of the breakdown of newsprint over time, that can be a very rapid decay. Whereas if we look at, a very well-made rag paper from the mid-19th century, oftentimes that rate of decay is much slower than some other materials from sort of modern times, if you will. But again, that reaction rate really depends on the level of heat and moisture that we're dealing with. At high temperatures and high moisture contents, that reaction will be much faster. And at low temperature and low moisture contents, we can slow down that rate of decay, although we can't ever truly stop it. Mechanical decay is a little bit different. Mechanical decay is all about the relationship of an object with its surrounding environment and the movement of water vapor in and out of any particular hygroscopic material. So if we have a material that is able to absorb moisture or adsorb or desorb moisture, what's going to happen is that material over time will come into equilibrium with the environment surrounding it. And that may be at a very high relative humidity, or it may be at a relatively low relative humidity. It just depends on what that condition is. And these materials will respond differently. One thing that we have learned over time, and this is the materials research that happens in the preservation and conservation field, is that different types of media absorb moisture at different rates. Some are very rapid, some are relatively slow, and the way that we store those, or the way that we house those, can play an impact on that as well. But when we have compound objects, or when we have materials that are made of different component parts, we see that stress occurs in different places. In the case of this vellum book here, we see that the stress really has occurred there at that bottom right corner, where just because of dry conditions and low relative humidity, the object slowly came to equilibration with that environment and finally just gave way. As the material shrunk and contracted on itself, there was no longer enough elasticity there for it to move without cracking. And we see the damage that occurs. Now the text block of that book is probably going to equilibrate and move at a very different rate. And what we want to think about here, things to just appreciate, is that when it comes to low RHs, what we're concerned about is that anything that naturally is able to take on moisture, anything that is hygroscopic again, as they lose moisture from that physical structure, the structure itself will shrink in on itself and contract and slowly become brittle. And really this happens, where the primary concern for a lot of materials, below 20% is the critical area. But oftentimes for collections environments in general, as we start to get below 30% relative humidity is where we're worried about this physical contraction occurring. And when we have high RH, those same objects that are able to take on and give off moisture are going to expand oftentimes beyond their natural, shall we say, physical limits. And they become soft and flexible and pliable. And this can actually cause permanent damage as well. It can actually disturb or damage that cellular bond that happens at the base level of that component or that material. And as that happens, we see materials that become deformed or they become misshapen. If you've ever dropped a book in water and seen it dry out, it doesn't dry out to its original form or its original shape. We see the wave, we see the different deformations that occur. And that's because that moisture attack, if you will, on that cellular structure was so great that it couldn't revert back to its original shape. And where we're concerned about this really is anytime we get generally above 65% is where the critical range begins to occur for a lot of materials. But again, as more of a general scope, when we're looking at collections media and collections that we hold in cultural institutions, anything above 60%, and we should start to get a little bit nervous about mechanical damage and potential expansion of materials. Biological, again, is also primarily dependent upon moisture content within a particular environment. And by moisture content, again, we're not talking so much about dew point, but about relative humidity and the relative saturation of the environment. But biological decay is caused by living organisms. It's not quite the same as the dog ate my homework, but it's that idea that there is a living biological organism that is attacking the organic media that we are working with. And this often falls into the categories of molds, mildews, or insects are the ones that come to mind, but it also includes rat damage or any other sort of mammal or biological attack, if you will. And temperature does play a role here, but primarily we're worried, as I said, about moisture conditions. Really, what temperature has going for it in this particular circumstance is that it can help determine the likelihood, if you will. And at higher temperatures, or at least moderately warm temperatures, it's far more likely that we're going to see issues with mold. It's far more likely oftentimes that we will see issues with biological attack in terms of insects or pests. But as we drop temperature, the rate of decay or the rate of that mold growth reduces, as does the activity level of a lot of our other pest concerns. Finally, we'll talk a little bit just here about metal corrosion. And technically, metal corrosion is a form of chemical decay, but we treat it a little bit differently because it's truly a moisture-driven process rather than temperature. And when we talk about corrosion, really what we're approaching here is the idea of oxidizable metals. We're talking about rust or tarnish. There's a family of metals that we run into very commonly in collection situations. This can range from silver to iron to bronze and to copper. And all of these have sort of a different means of corroding or a different result of corrosion that we see. And largely these occur as a result of high RHs. We're concerned at about 55% or greater, give or take. And this process can happen or can be moved along, if you will, by the presence of different types of pollutions or salts or dust or oils. If you've ever noticed on silver plate before, the first place that you begin to see tarnish is where there's a fingerprint on the silver. And that's just an indication that the tarnishing of the corrosion process has happened a little more radically or a little more rapidly in the presence of that oil and the presence of that biological material from the oils that are contained in the fingerprint itself. To talk about standards for a few minutes, and this is to introduce the idea of, what have we been working with? Where have we been in this field in the past, and what is it that we define as the appropriate levels? Really, over the past 3 to 4 decades, we've come to this agreement throughout the field that we're looking generally at this idea of a human comfort condition, roughly 70 degrees and 50%, with very little fluctuation. That this should be a steady control environment, a flatline environment, if you will, and that we're worried about short-term fluctuations. We're really concerned about that environment moving around and conditions changing. One of the other things that plays into this is that we generally require constant airflow throughout a collection space. And these are ideas or things that have been accepted as a standard for a long time in our different professional organizations or institutions. And one thing that we want to approach is, where did this come from, or how might it be a little bit different now? Largely, this approach originated, if you will, in Britain. It was pioneering work at the British Museum from Harold Plenderleith in the 1950s, or Garry Thomson studies at the National Gallery in the late 1970s and early 1980s that were kind of the basis of where this came from. Although it's interesting, if you go back a little bit, neither one of them actually ever came out and said that exactly flatline 70-50 was the best condition for preservation as we go through. Plenderleith in '56 really was the first person to emphasize environment as being a central concept to preservation, looking at it from a preventive approach and thinking about it in terms of needing particular environments to slow down the rate of decay of the materials that we're working with. And he came right at it and said, look, what we have to control, or what we should have in his environment, really should be determined by the nature of the collections and the types of decay that we're concerned about. But as he delved into it a little bit further and got specifically into paintings, and here's where we start to see specific numbers being put out, is that for painting specifically, we should want exactly 58% relative humidity and 63 degrees Fahrenheit. There it is. Line, there's one definition of a standard. Now, Thomson, a few decades later, as Thomson was looking at it in 1978, this is really foreshadowing in a lot of ways. He was looking at it, and notice underneath where he says, that the temperature must be controlled to control relative humidity. Well, all right, so that has something to do, if you will, maybe he's talking about conservation heating in a sense at that point, but the level is dictated by human comfort. Here's this first idea that the human occupants in many ways can be the larger factor in terms of determining a preservation environment than the collection itself, or than the collection preservation. And it's interesting too, in 1978, Thomson is already addressing this idea of sustainability and recommending that different seasonal set points should be used for the sake of fuel economy. We might have different summer and winter conditions. But notice there that Thomson provides for temperature a range. He's looking at going as low oftentimes as 65 degrees in the wintertime and as high as 77 degrees Fahrenheit in the summertime, anywhere from 18C to 25C, which is a relatively broad band, and really, when it comes right down to it, far broader than the traditional 70 degrees plus or minus 2 that we oftentimes interpret that as in today's definition of the standard and today's approach to it. Now below, when he's talking about relative humidity, and notice that he is talking about this constant provision for relative humidity, that day and night throughout the year we should be 50 to 55% plus or minus 5%. So if we define this as 45 to 60%, again, here's a fairly broad band that Thomson is advocating for in 1978, where depending on the collection, we may want that to be a little bit higher or lower, but he's saying that in a mixed environment, we can accept this broad range between 45 and 60. And again, I want to reflect a little bit on the idea that this is far different from our current understanding when we define relative humidity control, or at least as we have in the past couple of decades, is 50% plus or minus 3% or plus or minus 5%. Now in '86, Thomson came back in the second edition of the museum environment and made the comment that, really that standard specification of plus or minus 4 or 5% in RH control, this is great, is based more on what we can reasonably expect the equipment to do than on any deep knowledge of the effect of small variations of the exhibit. Which is just to say that really that standard, or that definition of plus or minus 4%, plus or minus 4 or 5% in RH, has to do with what the mechanical system is capable of, or what we have the mechanical equipment to control, as opposed to knowing anything about how the collection actually responds to those to those conditions. The lesson here really is that in the late 1970s to the mid-1980s, a lot of the materials research that has been done since didn't exist at that time. We didn't have the information for how materials specifically reacted to different temperatures and different moisture contents. And, in 1986, they were doing the best that they could. And that's sort of an overarching theme in the idea behind preservation environment standards, is that at any given point, we're only as good as the research that we have available to us. We can only come up with numbers that are based on the best information that we have. And when the 70-50 standard, if you will, came about based on constant conditions and very tight control, a lot of that definition was based on not a lot of science, not a lot of materials research or science that had been done previous to that. And it was based here on this experience, if you will, at the British Museum and the National Gallery, where they have, a very unique climate condition of having a moderate climate that is naturally cool and damp, which is very different than what we deal with here in a lot of the United States. Their primary concerns were over dryness and making sure that they could get the relative humidity low enough. But they also worked in institutions that did not have modern mechanical systems. They didn't have full control over moisture conditions throughout the seasons. This was before data loggers. It was before they had the opportunity to really gather data and see fluctuation and how much a building fluctuated over time. They were really working at that time with thermometers, hygrothermographs to a certain degree. And again, as we said before, it was before this intensive study of materials and how materials actually respond to environmental conditions. The other aspect at play here is that it really did emphasize the art and the gallery exhibit side of what we do in this profession. So they weren't looking at storage areas, they were largely looking at materials that were on display and that required human comfort conditions for the sake of the patrons that would come through. And this is where we see some of that coming out. When we think about this 70-degree and 50% relative humidity standard, if you will, that also happens to be, in many ways, the defined standard for human comfort that mechanical engineers use to design environmental systems for buildings. So we're talking in many cases with 70 degrees and 50% as an idea of the standard for preservation matching the standard for human comfort, which, as the material research has been done and as we'll find, is really not the case. The collections need something almost entirely different, really, than what it is that we expect for human comfort conditions. The other thing that's going on here is that it's oriented toward mechanically sensitive materials, paintings and composite wooden objects, panel paintings, and looking at it and thinking about this mechanical expansion and contraction without a whole lot of knowledge or without a whole lot of research or science being available on the rates of chemical decay and what the impact of temperature and relative humidity conditions are on that process. So now that we had this standard, now that this, as Thomson's language and as his work in the 1986 second edition was sort of taken out and put into context, a lot of it actually was taken out of context in many ways. As we saw, he was kind of addressing this broader seasonal range of approach for environmental control, and we find that that really got boiled down to this 70-50 that we're dealing with currently and today in many common designs. The result of that is that there was a slew of building and really a movement within our profession, within the idea of preservation and conservation, to achieve this ideal standard of 70 degrees and 50%. And we spent in the field, in many ways, the better part of 15 to 20 years fighting for that, building buildings that were meant to use mechanical systems to control very tight conditions, flatline conditions in many cases for 70 degrees and 50% relative humidity, that were extremely energy intensive. And the argument, or what we advocated for in the field at that time, was that this is what's necessary for preservation, and therefore the energy costs just have to be pushed off to the side. We have to swallow that cost. We have to deal with the fact that it's going to take a lot of investment and a lot of money, because in order to make our materials last, that's what we need. And as we go out now and we think about some of the research that's been conducted and performed since, we realize that in many ways we may have been a little bit off. This was before the period where we started doing research on brittle paper awareness in the 1980s. Really, a lot of this hadn't spread so far. And the recognition as it came down to it was that a lot of our organic materials, when we're talking about library and archive media, deteriorate through these chemical reactions. They deteriorate based on the level of temperature and relative humidity in the environment where they're stored. And that those two factors together determine that rate of decay. And at high temperatures and high RHs, things are going to decay more rapidly. As we moved on into the 90s, there was a lot more research being done about materials' response to different levels of relative humidity. At the Smithsonian in the mid-1990s, Marion Mecklenburg, David Earhart, Charlie Tomosa, and some other folks were really looking at, in particular, paintings for a large part. We're looking at paintings and thinking about, well, what is the actual safe range of RH conditions that these materials can withstand? And what they found was that the elastic range, or the safe range for storage, where they fully equilibrated to a particular condition without a permanent damage being caused to the object, where they could come back to a different RH and not have any permanent decay, that range of RH was much wider than what was previously accepted or previously understood. And that it came down to, really, for most of the media that they studied, there was sort of this broad category for a lot of it that between 30% relative humidity and 60% relative humidity, much of the media that they tested was able to behave elastically within that range. And not only was that range safe, but that the rate of fluctuation within that range was safe as well. So essentially it came down to, in their research, that between 30 and 60%, you could bounce in and around those two extremes as often as you wanted to, between 30 and 60, and be within that elastic range of movement for a particular object or for a particular media. which was a wholly different understanding of mechanical behavior and mechanical decay than what we had before. And as such, it wasn't immediately accepted. It wasn't something that was adopted at the time. And it was only about a decade later that really it started to take on and catch speed a little bit and think about, hey, wait a minute, this might mean something, and it changes the way that we approach it. Here at IPI, we've been doing research on equilibration rates and how long it actually takes materials to feel a temperature or RH change. A lot of our research on equilibration is taking place between the late 1990s and 2003, and even now on up into the present. We just completed another 3-year project on the rate of equilibration of library and archive materials. And where this comes into play and what it is that we're concerned about in this particular application is that if we make a change in the relative humidity in a particular environment, how long does it take the material to actually feel that? It's a fairly slow process. When we studied it for temperature, adjusting to that change in temperature, we found out that that thermal equilibration, that movement or that ability of the object to adjust to a temperature change happened relatively quickly. Most materials adjusted to that change in temperature in just a matter of hours. So when we're looking at overnight changes or day-night changes in terms of environmental conditions and temperature, objects would feel that, and they would feel that fairly rapidly. That amount of time was influenced by the amount of the exposed area of the object and the object's thermal mass. But when we started doing the research for relative humidity, we found something entirely different. And that's that movement of moisture and the equilibration rate for moisture in and out of most materials occurs relatively slowly. And most materials will adjust to a change in RH really in a matter of days or weeks as opposed to hours. Where this comes into play is thinking about, well, what is the concern or what is the danger of rapid fluctuation in RH levels? And it turns out that maybe it's not as great as we once thought it was. Now, it doesn't apply to all media. There is still some sensitive media that we have to be concerned with where the surface will equilibrate relatively quickly. But in general, when we're looking at library and archive collections or in materials that are stored in boxes or that are very densely packed on shelving, when we think about the time of equilibration or the time of adjustment, is we realize that it's influenced by the size and the amount of surface area as well as the temperature that's surrounding it. We find that this is quite a slow process, and for some materials can take as long as several months. Recently, as we go through, what we find is that as we're studying to define the safe RH limits for different museum objects, as we said, the result of this is that these tight tolerances really become de-emphasized, that there's no benefit, we don't gain anything by staying within this 50% plus or minus 3 or 5 range. If anything, we spend an awful lot of money to create it, but we don't see a preservation benefit from it for the majority of our collections materials. And that these wider limits, which, by the way, don't look all that different in many ways from what it is that Thomson was suggesting back in the 1980s. We've learned that they can go a little bit lower. But this 30% to 60% for a lot of materials is really acceptable, especially when it comes down to library and archives. It's the extremes that we want to be careful of. It's that beyond 60%, beyond 30%, where if allowed to equilibrate, the media may see permanent damage in terms of different physical shape. Now as we move forward into it in the 2000s, the late 1990s and 2000s, now we start to see that this idea of sustainability is coming into it, and this idea of thinking about the risk to collections when we're managing preservation environments. Specifically, Stefan Mikowski and Robert Waller have done some work in sort of that risk management perspective, and they're approaching it and saying, look, we need to look at this on a large-scale basis. We need to think about what type of collection and material we're working with. We need to look at the outdoor climate and what risk the climate presents to the material within a particular space or building. We need to understand what the tolerance is of the material itself, but we also need to understand what the building characteristics are and what it is about the architecture itself that may be positive or negative to the overall risk that is placed on this material. And when we think about it beyond that and start thinking about energy consumption and start thinking about sustainability, we've done research and work here at IPI, but that's also been, work has also been done by Michael Henry and Jerry Padani at the Getty Conservation Institute, among others. For looking at it and thinking about when we understand now that these ranges of decay, or these limits, if you will, in terms of temperature and relative humidity, are different from what we defined before, how does that create opportunities for us in terms of looking at environmental control and looking at mechanical control? And how can we go about creating what we now understand to be appropriate preservation environments in a more sustainable manner? And this requires really that approach that we've been talking about of active environmental management, rather than simply having a set it and forget it approach where we decide that there's a particular set point that we need, we set that set point and walk away from it, and the system just does its job. Now we're looking at it and thinking, well, maybe there are ways that we can do this in different manners seasonally, or we can have day-night differences, or there are different quantities of air that we can provide at different times, or how necessary is outside air. Or we can look at different opportunities based on this better understanding and research on materials' reaction to environmental conditions. And a lot of this really actually came to the forefront, if you will, in 2012. The British Standards Institute released PAS 198, and it was a document that is entirely different from anything that came before it. And it's something, they brought in a lot of different voices, a lot of different participation on this particular project. But what PAS 198 really encompasses is this general approach to thinking about a standard or thinking about an approach to environmental control and preservation environments that is not about a single prescriptive solution, that is not about a single set point and saying, here is the best condition for your collections to be in. And rather than that, rather than just giving a number and saying, everybody do this, it approaches it from the perspective of, well, the right answer is going to be a little bit different for each institution that's out there. And it's based on what your sustainability goals are. It's based on accountability. It's based on what your collections needs are. It's based on what your infrastructure and what your institution is capable of. It requires environmental monitoring. It requires knowing what your conditions are and knowing what your expectations are. So really it's following this overall optimization procedure in many ways. So it's a good reference now. There are different changes that are also coming about throughout the international community in this as well. For starters, ISO is starting to look at making some adjustments to some of its standards regarding storage environments and archival storage. So we'll see where those go in the next few years. But to sum it up, what we really understand now is that that old standard of 70 degrees Fahrenheit and 50% RH with minimal fluctuation really is expensive to maintain and is just plain not ideal. At that particular condition, the rate of chemical decay is far more rapid than we would like to see it. Our goal overall for collections environments needs to be to maintain cooler temperatures and low to moderate relative humidities to slow that rate of chemical decay and to make sure that we're within a safe band of RH conditions for mechanical movement and mechanical decay in collections. And as we said before, most materials, what we found is that fluctuations can be held between 30% and 60% relatively safely from a mechanical approach. But what we have to worry about, what are these extremes and where do we have to move from here? This is sort of that risk approach. What are the general risks and what do we have to consider for different media types? And we want to focus again on those extremes in collection vulnerabilities. So we're worried about the sustained periods of dampness and dryness and sustained periods of heat. And we want to think about it in terms of what are the media in the collection that are going to be most susceptible to this. When it comes to chemical decay, primarily we're worried about hot, damp conditions. We want to be able to avoid those. Any sustained high temperature is going to increase that rate of chemical decay. And our goal here really is to lower the temperature in order to slow down that rate. Now, one trick and one thing that we have to keep in mind is that RH does play a role in that rate of chemical decay, and in general, from a chemical perspective, the lower the relative humidity, the slower the rate of decay. That being said, this is where it becomes kind of a balancing act. We have to balance the needs of chemical preservation with the needs of the concerns for mechanical preservation as well. So we can't make the condition, the RH condition, too dry, or else we might cause mechanical damage to the object, even when we're trying to slow down that rate of chemical decay. It's the organics that we're concerned about when it comes to this chemical process, papers, woods, leathers. You get the idea, film as well. And it's anything that is going to spontaneously degrade or decay over time. And as we said before, metal corrosion is a part of this process. And also some calcareous materials, such as limestone, can be susceptible to different forms of chemical decay. Now, when we're thinking mechanical decay, what are the limits that we're worried about? We're worried about those very dry conditions. We're worried about RHs starting below 30%, but really getting concerned below 25 and 20% RH for long enough periods of time where materials can come to full equilibration. Now, a vellum cover on a book is going to equilibrate to a dry condition fairly rapidly, and we have to be concerned about that. Other materials may equilibrate a little bit more slowly, and we just have to take that into account. Very damp conditions, above 60 to 65% for weeks on end, means that materials will equilibrate and will expand over time and go beyond those elastic bounds and essentially cause permanent mechanical damage in terms of the item structure. And looking at that, those repeated excursions between extremes, this is what we see in seasonal behavior between, if you will, or in movements from wet seasons to dry seasons, where we have prolonged periods of high relative humidity that is followed some period of time later by long periods of low relative humidity. And this movement between those extremes creates a lot of physical stress on an object, particularly when we look at compound objects and we look at the joining process that is used to put those materials together. What are we looking at? What is vulnerable? Again, it's any hygroscopic materials that react to those changes in moisture in the air. Paper, woods, leathers all come to mind, but oftentimes what we think about when we're looking at mechanical decay are things that are composite media, looking at things like furniture and paintings. Cracking in a painting in an oil on canvas is not an uncommon occurrence throughout North America and Europe. It's something that unfortunately is fairly common. And the loosening of joints or the loosening of veneers on furniture due to moisture condition fluctuation throughout seasons is also something that we're very familiar with as well. So this is what we want to watch for. And again, it's anything that we move outside of those generally safe ranges of about 30% to 60% for most materials that we want to watch. When we think about biological decay, anything above 65%, we're going to begin increasing that likelihood of mold growth. As a general rule, when we hit 70% relative humidity in the field, we're starting to look for vegetative mold growth within collection spaces. And for insects and other biological pests, if you will, we start to get concerned when the RH goes above 50% and the temperatures are warm. Now, that's just to say that we always have to be careful about infestation or insect problems. But it is to say that in general, if we can keep the moisture content or the RH in a space lower, it is going to reduce the amount of issue that we have with pest problems as well. One thing to keep in mind is that if we try to improve conditions by cooling, just controlling the temperature of the space and lowering the temperature condition without having adequate moisture control, if we still have too high of a dew point, remember, as we lower that temperature at one particular dew point, the relative humidity will go up. And it does happen, unfortunately, fairly often that institutions will try to achieve a low temperature to get a better rate of chemical decay or a slower rate of chemical decay and have better biological conditions, but in doing so raise the relative humidity to an unsafe level. And you see circumstances and conditions where people have dropped temperature down to 58 degrees in a space and have grown mold because the RH spiked up to 80% for several weeks. So do keep that in mind, that it's not just temperature control, you have to look at the moisture control as well. It's the organics that we're particularly concerned with when we talk about vulnerabilities and what we have to do. And again, looking at mold growth and looking at mold decay, we're concerned with staining, but what it comes down to is that the mold is actually actively digesting the collection. And this is a permanent loss. It's not something we can clean or get back. Corrosion, what do we have to worry about? Typically, it's looking at any RH levels above 55%. That is a general rule. It's sort of a warning range when we're concerned about different types of oxidizable metals. And some of these corrosive examples are fairly obvious, if you will. Rust on iron materials or tarnish on silver are two things that we run across for a fair amount if you see a patina on copper or bronze. But one thing that oftentimes gets overlooked is that when we're working with black and white photographic materials, silver is the image base in that particular photography process. And that silver is equally as susceptible to corrosion over time as any other plate silver that we might be looking at. So if we're in a high relative humidity environment, over time we're going to see what happens in what we refer to as silver mirroring that you can see in this image on the right, which is the breakdown of that filamentary silver due to high RH conditions. And as that silver breaks down, it gains more surface area and we start to see loss of image density and quality throughout the photograph. The vulnerabilities are, again, just kind of widespread, and oftentimes what happens is that these are component materials within an overall object. So we may look at this saddle that we're looking at on the upper right-hand side and think that it's primarily leather and treat it as essentially an organic without thinking about the rivets or without thinking about the metal embellishments that may be or the trim that may be located on it that are going to react entirely differently through a corrosive process. thinking about it in terms of control and thinking about it in terms of just introducing this idea that we might want to create the environment a particular way, there are things that we need to keep in mind. We want to approach this as a risk-based idea. We want to be able to try and deal with these temperature and relative humidity extremes and set our definitions and our limits for where we don't want to be and make sure that we don't go beyond certain maximums and minimums. And we want to be able to identify which materials within the collection are most vulnerable. The key here really is that we need to do the best that we can with what it is that we have. Throughout this entire process and throughout the webinar series, we're not going to be advocating necessarily for a lot of capital changes or capital improvements. Instead, it's recognizing what your own system and institutional capability is and working to achieve the best efficiency or the best possible result from that media or from that equipment. And we'll talk a little bit more about that as we get into some of the other webinars. But as we approach this, one thing that we want to keep in mind is that our indoor conditions largely originate from outside. We don't live in a vacuum inside of our buildings, and our air all has to come from someplace. Typically, we bring it in on purpose inside of a building. So we're dealing with the outdoor climate first and foremost. And then we have a series of different buffering capabilities that happen before we wind up with a particular environment inside of a room. The building envelope is going to do something for us, depending on how well it's insulated or constructed. Storage enclosures we'll talk about a little bit more. But it's just to say that oftentimes they don't give us the same level of buffering that we might expect. And then in the end, it's the mechanical system, if we have one, that we expect to really put the fine-tuned control on what we expect and want that environment to be. And as I said before, we have a lot of folks hopefully joining us today from around the world, and we're all dealing with something a little bit different, right? We're all either dealing, sometimes we have hot summers and cold winters, sometimes we have high moisture periods, sometimes we have very low moisture periods. Other places are in an arid environment year-round or in a wet environment year-round. So what we talk about, we're going to try and apply as much as we can to different types of scenarios, but oftentimes the idea here is to take some of these ideas and think about how they might apply to the climate zone where you live. And the general theme here that I think we've all come to expect is that we can't control the outdoor climate. Oftentimes we can't even predict it, let alone control it. So we're dealing with what it is that we have. In some cases, different places have it a lot harder than others. Again, as we said, all the air coming into the building comes in from outside. And our goal for the preservation environment, or what it is that we've stated that we need to do, is to take that outside air and think about it in terms of how do we make it the appropriate temperature and relative humidity that we want. And oftentimes that means that we have to either add moisture or remove moisture from that environment. It can be, if we're not careful, a very mechanically intensive process. So that's the approach that we want to take of trying to think about and ensure that we're not doing any more work than we absolutely have to. The goal here is to try and figure out what we can do to make an environment that is as passive as we can possibly make it and use the mechanical system to trim and make sure that we don't go into the extremes. I know we're running a little bit short on time here, so just bear with me and we'll get through the rest of this in a few minutes. But we really have limited control over the building envelope. One thing we have to account for it as a factor, and unless we're working with new construction, you kind of have to work with what you got. But one thing is to understand what it is that the envelope is capable of. If we're in an older building, it's a lot harder for that building to provide any buffering capability based on the outside weather conditions. And think about and talk about with your facilities staff what it is that your building is capable of doing. Opportunities for control, sort of passive approaches, if you will. You can limit the solar gain in spaces by using shades and shutters on buildings or on windows. The ideal situation in storage environments oftentimes is to have no windows whatsoever, just to reduce that light pollution and reduce the chance of any radiant energy getting into the space. We want to try and reduce heat gain and heat loss by adding insulation to the building going through. And we need to keep in mind where the moisture in the building is coming from. So some of it is fairly obvious. We need to think about repairing leaks or replacing damaged gutters. But there are also aspects in terms of thinking about how water is routed around the building. Does it go underneath your building? Are you worried about groundwater coming up through the basement, or can you move it out away from the building so that that's less of an issue? The other thing that we'll talk about more going on through the series is just considering the idea of outside air and how much we bring into a particular space. Because when we bring in the outside air, we're purposefully bringing in temperature, the moisture content, and bringing in also pollutants with that to bring into the storage environment. And if we're working in a specific storage area, oftentimes the need for fresh air, if there's no human occupation, is far less than what we've previously understood. Storage enclosures are great for a lot of things. They're great for intellectual control of materials. They're great for protecting against pollution and different particulates and dust. But when it comes to acting as a buffer for temperature and relative humidity changes and temperature and relative humidity conditions within a particular environment, most of the time our storage enclosures don't provide an awful lot of buffering capability, especially not when we're talking about boxes and envelopes. Now there are situations when we get into cabinetry, when we get into gasketed cabinetry, where those truly can slow down the rate of equilibration, the rate of moisture and temperature movement throughout an environment. So if you're in a situation where the building itself may not have a lot of capability to control conditions, then looking at heavy duty or looking at, shall we say, well-designed cabinetry with a lot of ability for buffering may be a good passive solution when you're thinking about how to mitigate moisture levels within a particular collection environment. And again, as we go through, the primary thing that we come down to here is that enclosures have their place, but most of the time it's not as a replacement for environmental control or mechanical control of a particular space. And that's something that we have to think about, is that where mechanical control is available, it's using it appropriately. And where it isn't available, we have to find other solutions oftentimes to try and make up for that or at least mitigate those issues as much as possible. Mechanical systems in general, we refer to this as the loop. And basically the idea is that we're taking air that has been worked on in one part of the building and taking it through a series of different processes, and we're moving that conditioned air off to another space where it provides the work. It either cools up the space or cools down the space or warms it up, and that air then gets sent back to the air handling unit again to be reworked. As that loop moves through a typical AHU, we can do a couple of different processes. We can raise the temperature, lower the temperature. We can either increase or decrease your humidity levels. We can increase or decrease the moisture content of the air going through. The filters within the system can remove particulates for us, and outside air can be added and or removed. Really, this new thinking about environmental standards, what it comes down to is it gives us this opportunity to rethink that mechanical system operation. The nice thing about expanding this approach or expanding our understanding of what environmental conditions are appropriate is that it means that we can start to think about operation and start to think about operating times, start to think about set points and different types of control. For system operation, it can be energy saving for us. Some of these examples may include looking at system shutdowns or may just include looking at different seasonal set points as we go through. So the summary for this is that, as we go through and think about this overview, what I hope has come across today, and I do apologize that we're running a little bit late, but what I hope has come through today is that it is possible to balance what we need for collections preservation with what our sustainability and energy reduction goals might be. The idea here is that we want to look at these different factors, at these, these 4 or 5 basic ideas. We're going to spend more time on these as we go through the rest of the webinars. And what we're going to try and provide or try to lay out is to achieve this basic understanding of how it is that heat and moisture contribute to decay. We want to look at those environmental conditions a little more closely and talk about how materials degrade over time. We'll spend a lot of time on that in the next session. We're thinking about the new standards for environmental management based on these new ideas of research that have come about in the last couple of decades. And we're going to come at that from a couple of different directions in the webinars in the coming months. We want to think about these extremes of temperature and relative humidity and the impact on different collection materials. And we also want to think about using that data-driven team approach in terms of controlling the environment a little bit better and understanding what the impact and what the consequences are of certain decisions. We're going to spend some time moving forward as we look at the future webinars talking about different ideas for mechanical control and how the standards change what we do in terms of systems operation. And we'll talk a little bit just about what the overall idea or the overall approach to trying to achieve optimization and sustainability is, with some specific suggestions or practices that we might be able to take. Now, for upcoming webinars, we've got a list here. The list is also available online. Please do feel free to go into that and take a look and think about what might be appropriate and what might be useful to you. We will go into a lot of specifics here, so I do apologize that this was today largely an overview and an introduction, but I hope it at least piqued your interest to come back and join us for these future webinars as well. What we'll be doing coming on up in March is we'll be talking a little bit more about different categories of decay, looking at chemical decay, mechanical decay, biological and metal corrosion, and talking more specifically about what the consequences of that and how materials respond and what we have to be concerned about. We'll talk about the preservation metrics and how it is that we can go about quantifying and measuring different rates of decay, talking about roles of heat and moisture and the interaction of temperature and relative humidity. And really we'll be just spending a lot of time in terms of thinking about environmental extremes and talking a little bit more about dew point as well, although we'll discuss that in later webinars. The project website for this is ipisustainability.org. Please do feel free to visit. This webinar will be archived there as a viewable video. It will also be available on our YouTube video within probably just a couple of days. So if you have any questions or you need to go back to it, please do feel free. In just a few moments after the seminar is over, there will be a survey that goes out to everyone. Please do take just a couple of minutes and fill this out. It's something that is important to NEH. They appreciate having the feedback of people's reactions to what it is that we've been able to bring with their funding. And we appreciate the feedback as well. It does inform what we do from webinar to webinar. Now, I want to say that it is 3:31. Unfortunately, we went a little bit longer than I was hoping to. But if you have any questions, if anybody's willing to hang around, we can take 10 minutes or so and try to address a couple of questions that came in during the course of the webinar. Please feel free to send in any additional ones that you might have. And we'll pop those up and I'll try to address as many as we can here in the next 10 minutes or so. So feel free to send those on in. All right. Well, we've got a couple that have come in. We have a question that came in from Thomas Dietz. Thanks, Tom. For smaller institutions, maintaining 70 degrees Fahrenheit may be expensive in the summertime. What is the effect of slightly higher temperatures, say 72 to 74 degrees? It's a really good question, and it's a really good point. And that really is the basis of thinking about this optimal operation and thinking about what optimal is for different settings and different institutions. What it really comes down to is that you have to balance the institutional availability and what it is that you can do based on what it is that you have for a budget, based on what the collection needs. And oftentimes when we start looking at temperature set points in the summer, especially if you're in a temperate area of the world where you have cooler winters and have the opportunity to maybe drop temperature conditions in the wintertime, if the ability to cool to 70 degrees is beyond the budgetary limits of what the institution has, then increasing that summer set point to 72 degrees or 74 degrees is certainly a viable option to explore. You have to accept the fact that you're going to give up a little bit, probably in terms of preservation quality. Generally speaking, in terms of PI, we'll show dew point calculator later in the series, but you'll be sacrificing a little bit in terms of rate of chemical decay. Your chemical decay is going to speed up a little bit, but if you save money in the process, and it means that you're able to maintain the environment because of that, one thing to look for is that if you have to make a sacrifice in the summertime, move to the wintertime, or if you have a cooler period of the year, move to that time of the year and try to figure out whether or not you can take advantage of any savings there by maybe reducing the space temperature. Instead of holding 70 degrees in the winter months, if you can back it off to say 65, or back it off to even lower if you have limited hours or when you're closed. Just think about it as a yearly strategy, if you will. And rather than just accepting that we have to increase the temperature to 72 or 74 as opposed to 70 and accepting that loss, think about that as just part of your overall yearly approach, and how can we go about trying to improve then in another part of the year. It's not to say that you get that back. Once the damage is done, it is done. But there is something to be said for doing the best that we can in the periods where it costs us the least money, and trying to do as well as is financially reasonable or appropriate during the periods when it's much more expensive to do that. I hope that helped a little bit. We have another question that came in from Rosanna Kwan, and her question is, what would be an optimal solution for a climate that fluctuates from 15 to 25 degrees C all year long with an 85% relative humidity average? Wow. I'm going to guess that you're coming from maybe Latin America, Africa, South. It's hard to say. But yeah, that's awfully tricky. You're right. When you're working with an environment that has a very high year-round relative humidity, what it is that you want to try and do, and this is actually very similar to an issue that we're having on an island off the coast of Maine right now with another partner that we're working with, is that you have to consider what the requirements are for different aspects of the building and different aspects of the collection. Oftentimes the goal is just to try, if you're working in a passive situation where you don't have a lot of mechanical control, we want to try and mitigate the moisture issues as much as possible with non-mechanical means. So if you can look at installation of vapor barriers, if you can look at sealing up a structure more appropriately so that it slows down the rate of moisture migration from the outside to the inside, if you can reduce the amount of outside air that is introduced into the interior environment, all of those are going to be helpful to trying to reduce that overall interior moisture content in the space. And then as that occurs, what you need to look at from there is considering what are the materials that you're trying to care for. I don't know just from your particular question, but what are the materials that you're trying to care for, and what are the safe ranges or what are the most appropriate ranges for that material? If you have a collection that is new to that environment, that is particularly susceptible to high levels of relative humidity, then maybe you want to approach it, if you're looking at non-mechanical solutions, maybe you need to approach that or think about it in terms of, again, a very tightly sealed or gasketed cabinet with silica inside of it that's going to try and keep a small micro environment of low relative humidity conditions. If you're looking at a mechanically controlled space, you try to reduce the size of that mechanically controlled space as much as possible in order to reduce the energy component that's involved, and think about very efficient or very compact storage solutions that are going to allow you to do a lot of work and a lot of creating an appropriate environment in as small a footprint as is possible. So it's hard to get into a lot of specifics without knowing exactly what your situation is. And please do feel free to write in separately and ask if you'd like to. But it is to say that that is a challenge, and it does come back to take advantage of what outdoors gives you when you can. So those periods of the year where you have 15 degrees C that you're working with, which is relatively cooler, at least than your hot season it sounds like, try to take advantage of that as much as possible. Make sure that there's no artificial heat being provided to the environment. Even if it's not mechanical in nature, try to reduce lighting operation or try to reduce heat gain through windows or through different sources of radiant gain. So, I'm sorry that might be a little bit vague for an answer, but there are things that you can consider and really just think about the specifics of what the need is and what the concerns are. We have another one here from Catherine Corman, and she's asking, will you address the risks of temperature fluctuations around freezing point later in the series? Catherine, we'll address that a little bit as we go through, and it varies for different media types. We'll get into a little bit in terms of photographic media and different media that should not be frozen that we want to be careful of in terms of long-term permanent storage conditions. We can also talk about it a little bit just in terms of some different natural history issues that come up. In terms of specific temperature fluctuations around freezing point, if you'd like to write in with a little more detail of what your own situation is, or if there's a little more specificity to the question, we can see if that's something that we can address. And go from there. Another has come in from Catherine Unch. The question is, has anyone done studies on the costs of maintaining climates as compared to costs of devalued collections due to deterioration and or the costs of repairs? That's a really good question, Catherine, and to be honest, it's not one that I've seen. One thing that I will say is that there's more and more information out there. We do some work in it, as well as some other institutions around the world. They're doing more work in terms of evaluating what the cost patterns are and what the energy costs are of maintaining particular preservation environments in given settings. It's a hard thing to generalize because buildings and energy rates do vary widely from location to location, especially as we look at global impacts. But in terms of looking at the cost of devalued collections based on deterioration and or the cost of repairs, the cost of repairs is a really good question, and that's something that might be a good opportunity to partner with the conservation staff at some point in time, thinking about labor and thinking about the time that is put into potential environmentally induced damage and the repair or the recovery from that. Devalued collections is another approach or another aspect of the question that is probably a little bit trickier, and that's something that I don't have a lot of experience with. It's something that in terms of thinking about, and I think where my mind would naturally go with this is thinking about it in terms of what would an insurance company's reaction be to damage sustained to collections, and how is it that they may change, say, the valuation of a particular collection. And I've never had that conversation with an insurance representative before, largely because we don't have our own collection that is insured, so it's not something that we have to deal with on a daily basis. But again, I think it's a worthwhile question and something to consider for museums that are working with insurance scenarios where they're working with different adjusters and looking at rates and looking at overall values of collections. That might be a very worthwhile conversation to have in terms of how that valuation or what the impact of any environmental damage or long-term decay might have on that particular number. And that's what I have right now. We're at 3:40. We're about 10 minutes over. Thank you, everybody, for your patience and for sticking with us. It looks like most of you did stick around with us. I do appreciate that. Again, my apologies for going over, but I hope everybody's enjoyed it. It's been a fun hour and a half for us. We'll be back to join you again here in March. Please do join us again, and thank you very much. Have a great rest of your afternoon, evening, night, whatever time of day it might be wherever you are.